In this video, we're going to take a look at a couple of examples of how to determine whether S is a basis for an indicated vector space. Given this particular set S, we need to determine whether it is a basis for R3. By definition, a set S is a basis for V if S spans V and S is also linearly independent. Let's first try to show that our set spans R3. We'll do this by letting X represent an arbitrary vector where X equals x1, x2, x sub 3. So letting X be this arbitrary vector in R3, if we can show X to be linearly dependent, then we can find constants C sub 1, C sub 2, and C sub 3 that satisfy this equation in blue. We can rewrite this equation as a system where X sub 1 is equal to C sub 1, X sub 2 is equal to 5C sub 1 plus C sub 2, and X sub 3 is equal to 3C sub 1 plus 2C sub 2 plus 6C sub 3. Next, we can set up a coefficient matrix for the system and find the determinant. If the determinant is non-zero, then we will know that it has a unique solution and that S does span R3. So our coefficient matrix would be 1, 0, 0, 5, 1, 0, and 3, 2, 6. Using a graphing utility, the determinant is equal to 6, which is non-zero. Therefore, a unique solution exists, and S spans R3. Next, we need to determine whether the vectors are linearly independent. Again, we refer back to our system of equations and we consider our coefficient matrix for which we calculated the determinant. Since the determinant was non-zero, referring back to our system of equations, which we used to set up a coefficient matrix and find the determinant, because the determinant was non-zero, we know that the only solution is the trivial solution and that the vectors must be linearly dependent. And it follows that S is a basis for R3. Let's take a look at another example. Let's determine whether S is a basis for P sub 3, where S equals t cubed minus 2t squared plus 1, t squared minus 4, t cubed plus 2t, and 5t. Remember that the set S is a basis for a vector space V if S spans V and if S is linearly independent. So let's start by multiplying each polynomial in the set by a scalar A. So we have A sub 0 times t cubed minus 2t squared plus 1. And we'll add that to the next polynomial, which is multiplied by A sub 1. So we have A sub 1 times t squared minus 4 plus A sub 2 times 2 cubed, t cubed, plus 2t, plus A sub 3 times the polynomial 5t. Of the form given above, such that A sub 0, A sub 1, 2, and 3 are real numbers. We can test for linear independence by setting each polynomial equal to 0 and setting up a system of equations. If the solution to the system is trivial, then we will be able to conclude that the set S is linearly independent. Let's take a look at our system. We would have A sub 1 plus A sub 3 equals 0. And we get this from our coefficient to t cubed here. And actually this should be A sub 0 and A sub 2, where we get from the coefficients of t cubed and then also t cubed here. Then we have negative 2 A sub 0 plus A sub 1 equals 0. We have 2 A sub 2 plus 5 A sub 3 equal to 0. And finally, A sub 0 minus 4 A sub 1 equal to 0. If I set up a coefficient matrix, or in this case, let's set up an augmented matrix and find our solution using a graphing calculator, then it will look like this. On our graphing calculator, I would apply the reduced row echelon feature, which is found in Matrix, Math, and on the TI-84 it's letter B, RREF, And we do this after we enter our matrix under the Edit screen. And when we do this, our result yields the trivial solution. Since the system has only the trivial solution, we know that S is linearly independent. Therefore, since S is linearly independent, and from our earlier work we know that S spans P sub 3, we are able to conclude that S is a basis for P sub 3. So there you have a couple of examples on how to determine whether S is a basis for the indicated vector space. I hope you found the examples helpful, and we'll see you next time.